Hello students, welcome to the first video for G7. This entire unit is about similar triangles. So you just finished a lesson on congruent figures and congruent triangles, and now we're going to move on to something called similar figures and similar triangles. So the word we're really going to focus in on is this word, similar, okay? The definition here of similar polygons or similar figures is they are polygons that have corresponding angles that are congruent, which means they hold the same shape, and corresponding sides that are in proportion to one another, okay, which means they create a different size. So I want you to visualize like taking an original figure and enlarging it or making it smaller, like we did with dilations. Similar figures are dilated images of one another. Dilated images. So that means they have the same shape, since that part is congruent, but different size. One is an enlargement of the other. Okay, so same shape, their angles are congruent, but different size. One word we're going to use a lot, and we learned about it with dilations, is the term scale factor. Scale factor is the ratio between a pair of corresponding sides of similar polygons. It's how you're describing how much bigger or how much smaller one shape is in comparison to the other. Okay, so we're going to use these trapezoids as an example. We're also going to practice naming them. So check this out. Just like with congruent figures, when you are naming similar polygons, the vertices must be named in corresponding order. Man, there's all these things coming back from previous lessons. We talked about dilations earlier in the year. We've talked about how to name corresponding figures earlier in the year. We've talked about what it means to be corresponding in the same position earlier in the year, and it's kind of all coming together here. So let's take this small trapezoid as the original. I'm going to call this ABCD. Keep it simple. ABCD. And I'm going to call this bigger triangle EFGH. So if I want to say that the smaller trapezoid is similar to the bigger trapezoid, I'm going to want to come up with a similarity statement. Okay, a similarity statement is a lot like a congruent statement, except that it's matching up the two figures based on angle placement. Okay, so here I have angle A that's in correspondence with angle E. They're a match. Angle A is congruent to angle E. Angle B over here is in the same position or is corresponding to angle F. So angle B and angle F are a set of congruent corresponding parts. We've got C in the bottom right, congruent to G. And finally, that leaves us D, congruent to H. Okay, so I've written out all of the corresponding angles that are congruent to one another, and that is going to help me come up with the similarity statement. If I start, I'm just going to pick a crazy order for this first one. I'm going to say DCBA. If I'm talking about figure DCBA being similar to, here's our symbol for similar to, okay, it's just the top half of the congruent symbol. If I go in this order, I have to make sure to match up corresponding parts. So angle D, we've said, is congruent to angle H, so H would come first. C is congruent to angle G. B is congruent to angle F, and A is congruent to angle E. the order that you write your similarity statement in really does matter because you are showing what parts match up with each other. Something else we can do here is come up with corresponding sides. Now, be very careful. We're not talking about congruence anymore. So I cannot say that side AB is equal to side EF. That's not true. What I can say is that the sides are now proportional to one another. Okay, meaning if we double the size of AB to get to EF, then we would double the size of every side in the image. So I need to write my corresponding sides out as a proportion statement. So check this out. I'm going to start with side AB. The length from A to B can be compared to the length from E to F. That is a corresponding set of sides that I can write up as a fraction. Okay, that would be equal to, let's set up another set of corresponding parts. Side BC compared to side FG. Okay, now let's go with side CD. Side CD is the bottom of this trapezoid, and it can be compared to side HG. We're not saying they're equal. We're saying that their ratios are equal. I have one final comparison here. It'd be side AD compared to side EH. Okay, so what we've done here is we've got all of our angles that are congruent to one another. Remember, angles are congruent, and all of our sides that can be written as a giant proportion. Okay. Let's do a couple examples and see if this makes sense to you. Come on down. The question here is, are these figures similar? And if so, state the similarity statement and the scale factor. Okay, so there are two things to check to see if you have similarity. Number one thing to check is, are the angles congruent? That is the first question. Is there a set of corresponding congruent angles? Okay, so let's check that out with number one. Angle Q is a match with K, angle R is a match with J, and we can continue around this figure, and yes, there are congruent corresponding angles, so that is a go. Yes. The second thing to always look for is, are the sides proportional? Are the sides in proportion with each other? Okay, that's the second question. All right, so let's check out this proportion. Well, let's see. From Q to R is from a double angle mark to a single angle mark. So that side length is 20. I can compare that, okay, to K to J. K to J goes from a double angle mark to a single angle mark. So I'm saying the side length 20 can be compared with the side length 30. Those are corresponding parts. All right, let's set up a proportion here. Let's see if this is true. Another piece that would match each other would be over here, RS. RS is a match. That goes from a single to a double. So 16 for RS. And then on the right figure, a single to a double is 24. Now the question is, are these proportional? Do they reduce to the same thing? Okay, well, let's check it out. 20 over 30, you can divide both of these numbers by 10, and that would give you 2/3. 16 over 24 can both be reduced by 8. 16 divided by 8 is 2, and 24 divided by 8 is 3. So this is a true proportion. 2/3 is equal to 2/3. Okay, so over here, the two things for us to check were, are the angles congruent to one another, and are the sides proportional? If you can answer yes to both of those questions, then you do have a set of similar figures. So these are similar figures. So I'm going to write up a similarity statement. Now, when writing up a similarity statement, remember that order matters. You have to match up corresponding vertices. So I'm going to start with angle Q on the left. That has a double angle measure, and so does angle K. Those are corresponding vertices. I'm going to move up to angle R with a single measure, which would match J. Move down to S, which would match up with I. And finally move down to T, which would match up with H. When I write my similarity statement in this way, every vertex has a partner that can be matched up. The next question is, what's the scale factor? Well, I wrote this going from the figure on the left to the figure on the right. So I'm going from a smaller figure to a larger figure, this being the small figure, and KJIH being the larger figure. Okay, so when I write my scale factor, I have to write it as small on top and large on bottom. The smaller numbers on top and the larger numbers on bottom, because I wrote my similarity statement from small to large, so I need to write my scale factor from small to large. So if you check out the reduction of these two fractions over here, they both reduce to 2/3. That is our scale factor. Our scale factor is 2/3. And what we're saying is that figure QRST is 2/3 the size of figure KJIH. It's 2/3 as big as the larger figure. Now, if we flip-flopped our similarity statement, then we would have to flip-flop our scale factor, because we'd be saying something different. We'd be saying, if KJIH came first, we'd be saying that the larger figure is 3/2, 1.5 times bigger than the smaller figure. So this is explaining the amount that the figure grows or shrinks. Okay, let's try again. On this next image, remember there are two things we're looking for. The first thing we're always looking for is, are the angles congruent? Okay, that's the first thing. So I'm going to jot that down. Are the angles congruent? Is there corresponding congruent pairs? So let's take a look. On the left, I've got angles with a triple mark and angles with a quadruple mark. And on the right, I have singles and doubles. So before I even get started with all this proportional stuff, I can tell that these figures are not similar because we don't have 4 congruent angles from left to right. So I'm going to use this symbol. It's my similarity squiggle there with a slash through it, saying these are not similar to each other. These were similar, so I guess I could use that. But it's right there. Okay, so these are not similar figures. They do not have congruent angles. All right, let's try example 3 here. First things first. Okay, first things first is, are the angles congruent? That's an easy check. Are the angles congruent? So I've got G has 1 mark in it, V has 1 mark in it. F has 2 marks in it, W has 2 marks in it, E has 3 marks in it, U has 3 marks in it. So all 3 of the angles on the left are congruent to all 3 of the angles on the right. So this half of the requirement is fulfilled. There are congruent angles. The second half of the requirement is, are the sides proportional? Are the sides proportional? And that's where you got to do a little bit of fraction work here, okay? So I'm going to look over here at the left. I'm going to go from G to F. That's the side I'm going to focus on. That is from 1 angle mark to a double angle mark. So 21 matches up with V, 1 angle mark, to W. Okay? So that 21 can be compared to 28. All right, next, I need to set up all the proportions to make sure they all reduce. Let's see. Next, I'm going to go from 2 to 3. So I'm going to go this way, F to E. Oh, my pen stopped working. Okay, let's try this. From F to E. All right, so from F to E is 9. That goes from a double to a triple. So to follow that same pattern, double to triple, I'd be using the side length 12 from the right. All right, and I have one more to go. One more to go. From a triple to a single on the left has a side measure of 18. And from a triple to a single on the right has a side measure of 24. Now, it's my job, in order to know if these figures are completely in proportion with one another, it is my job to make sure that all three of these fractions reduce to the same thing. So let's do a little simplifying here. My first fraction, 21 and 28, can be reduced by 7. Reduced by 7. And 21 divided by 7 is 3. 28 divided by 7 is 4. Okay. Next, I've got 9 and 12. 9 and 12 can both be divided by 3. So I'm going to say reduced by 3. 9 divided by 3 is 3. 12 divided by 3 is 4. We're on to something. Lastly, I've got 18 and 24, and those can both be reduced by 6. 18 divided by 6 is 3, and 24 divided by 6 is 4. Boom, check it out. All three of these side ratios reduce to the same value. That value is, dun-da-da, the scale factor. It's the scale factor. We are saying that the smaller triangle, which I'm going to call GFE, is similar to the larger triangle VWU, and it is 3/4 the size. Now, make sure you understand how I'm getting these letters in the right spot. G and V both have 1 angle mark. F and W both have 2 angle marks. And E and U both have 3 angle marks. That's how this similarity statement came to be. And we are saying that figure GFE is 3/4 as big as figure VWU. Okay, so there's 3 examples there of how to decide if figures are similar. Okay, the 2 things to check are the angles congruent? And number 2, are the sides proportional? That is the definition of similarity. All right, flip your page with me and let's check out what's happening on the back. Okay, here on the back of our page, we're working a little bit differently. We are not trying to figure out if the figures are similar. Every single set of directions down the page tells us the polygons are similar. So it is a fact. They are similar, which means if they are similar, that means that the angles are congruent and the sides are proportional. Proportional, not congruent. The angles are congruent. The sides are proportional, which means one figure is an enlargement of the other. So let's take a look at how we might use this information to do some solving. All right, we're bringing some algebra back in. Check out example 1. It says for us to solve for x, y, and z. All right, I'm looking at this figure first, and I am going to find a set of corresponding parts that has no variable in it. Here's what I mean. If you look at the top of this figure, 15 and x match up. That's a number and a variable. That's not going to help me right away. If I look at the right, y and 5 match up. Okay, that's another variable and number. I'm looking for where 2 numbers match up, and I have it right here on the left. Okay, that is going to be kind of my anchor for this whole problem. I need to solve 3 separate proportions where I can figure out how much bigger figure 1 is than figure 2. So take a look at these two values, 20 and 10. 20 over 10. That reduces to 2. This is my scale factor. We are saying that figure 1 is twice as big as figure number 2. Okay, if this side measure is 20 and this side measure is 10, 20 is twice as big as 10. So that means every single side on this figure is double the length of the smaller figure. So let's set up some proportions to make sense of it. Here's the proportion for x. Okay, x up top here from E to F is corresponding with 15. Okay, those are a set of corresponding parts. So I can say, I'm going from left to right, figure left to figure right. 15 can be compared to x just as 20 can be compared to 10. Now this is one way to do it. I don't have to do it this way. I could use the scale factor value, but I'm just going to do this because I think it's very easy to set up. 15 goes with x, 20 goes with 10. Well, you've done your practice on how to solve proportions. You cross multiply. So 20 times x is 20x. 15 times 10 is 150. And now I need to divide both sides by 20 to get x all by itself. And I'm going to get 7.5. Let's see if that makes sense. 7.5. 20 is twice as big as 10. 15 is twice as big as 7.5. We're in proportion. Okay, let's try another one. Let's solve for y. Okay, the side with y is on the larger figure, so I'm going to put y on top. Remember, I'm working from left to right. Y matches up with 5, just as 20 matches up with 10. Now here in my fractions, the figure on the left is on the top of the fraction in the numerator. The figure on the right is in the bottom of my fraction. I'm working this direction from left to right. Okay, so I've got another opportunity to cross multiply. Y times 10 is 10y. 5 times 20 is 100. Divide by 10 on both sides. I'm going to get y equals 10. All right, double check and make sure that that makes sense. 20 is twice as big as 10. 10 is twice as big as 5. We are in proportion. All right, we've got one more here, last one. Okay, let's find a proportion that would solve for z. Okay, z is down here on the bottom. 30 is down here on the bottom. That's a set of corresponding parts. So I'm moving from left to right. 30 can be compared to z just as 20 can be compared to 10. Cross multiply. 20 times z is 20z. 30 times 10 is 300. Divide both sides by 20. And you're going to get z is equal to 15. All right, always check your work there. If z is 15, does the scale factor hold true? 20 is twice as big as 10. 30 is twice as big as 15. Now highlight these answers. Now you may be thinking, I could have done that without all of that proportion work. If you're telling me that 20 is twice as big as 10, I can do the rest in my head. 30 divided by 2 is 15. 15 divided by 2 is 7.5. Going the opposite way, 5 times 2 is 10. And that is absolutely fine. You can absolutely continue to do that work in your head. I encourage that. However, you're going to need some kind of method to solve when you run into something like this, where we have more algebra in the problem. Okay, so let's check out example 2 here. First of all, notice that the directions tell us that the two triangles are similar. They are similar. So we don't need to discover if they're similar or not. We are being told that they are similar. So if they are similar, that means their angles are congruent and their sides are proportional. That's what you get when you are given the information that figures are similar. You automatically know these two things. The angles are congruent and the sides are proportional. Now this problem has nothing to do with angles, okay? Everything to do with sides. So let's start that proportionality piece. Here we're only asked to solve for x. I'm going to highlight that side. The yellow side I've highlighted is corresponding to the side measure 5 on the smaller figure. They are in the same position. They're corresponding parts. So they can be compared in a fraction. 2x plus 9 and 5 are corresponding parts. Okay, we can set them equal to another set of corresponding parts. Now here we're looking at some isosceles triangles. We've got 35 and 35, and then we've got 7 and 7. So if the triangles are isosceles, you could pick either one of those sides. Even if they're not isosceles, you could pick either one of those sides. But let's check this out. I went from left to right again. So I'm moving in this direction. So I have to keep that pattern in my fraction. 2x plus 9 over 5 and 35 over 7. Okay, you may already know something here. 35 over 7 reduces to 5. Reduces to 5. So if 35 over 7 reduces to 5, this is the scale factor. We are saying that the figure on the left is 5 times bigger than the figure on the right. 5 times bigger. Okay, let's see what that does for us over here in our proportion. I need to solve for x. Cross multiply. Now, a little algebra help here. When you are cross multiplying something that's a binomial with two parts, you are taking the 7 and you're multiplying it by both of those parts. It's a big distribution problem. So it's going to look like this. It's not just 7 times 2x. It's 7 times the entire value. Now we need to distribute. 7 times 2x is 14x. 7 times 9 is 63. And 5 times 35 is 175. Now I need to solve for x, so I need to get x by itself. I'm going to start with subtracting 63 from both sides. That'll make the left side all variable, and it will make the right side all number. 175 take away 63 is going to leave me with 112. Now I need to get rid of the 14 attached to the x. That 14 is a multiplier, so I'm going to divide both sides by 14. That leaves me x all by itself on the left, and 112 divided by 14 is 8 on the right. So I'm getting x is equal to 8. Now, don't just believe your algebra. I mean, I feel like I do really good algebra, but I have to always check it. So I'm going to put this 8 back into the problem. 2 times 8 is 16, and 16 plus 9 is 25. Now go back to the scale factor for your check. Okay? If we are saying the scale factor is 5 and 35 is 5 times bigger than 7, then it has to be true here. Is 25 5 times bigger than 5? Yes, Yes, the figure on the left everything has to be proportional. So if I did all of this work and I plugged back in and I got 20 instead, 20 is only 4 times bigger than 5, whereas 35 is 5 times bigger than 5. So that would not be in proportion. They would not have the same scale factor. Okay, one more to go. I'm going to talk through this last one. I hope after 3 examples it's starting to make sense for you. I'm told here that the figures are similar. Yay, the figures are similar. Again, for the last time, what that means is that the angles are congruent. Angles are congruent, and that the sides are proportional. Sides are proportional. This is the new part for this unit, the proportionality piece, okay? So if the sides are proportional, I need to be able to set up a proportion. So in looking at this picture, I want to match up corresponding parts. Here's my x, my side with the variable. It is in a corresponding position to the side labeled 32. So my first fraction I can build is x plus 12 over 32. These are corresponding parts, so I can make a fraction out of them. Okay. The other values I'm given are 12, which corresponds to 16. So that's a corresponding pair. I'm moving from left to right, so the 12 goes on the top, the 16 goes on the bottom. Okay, so what I'm saying here is x plus 12 on the left can be compared to 32 because they're in the same position. 12 on the left can be compared to 16 because they're in the same position. And because the figures are similar, this is going to make equality. They are going to have an equal value. All right, so now for the solve. Flip back to algebra brain. You have to cross multiply here. This 16 is going to multiply the x plus 12, making a distribution. And this 12 is going to multiply with the 32. So here's my distribution. 16 times x is 16x. 16 times 12 is, using my calculator here, 192. On the right side, I've got 12 times 32, and I'm getting 384. So now I need to solve for x. I am going to subtract 192 from both sides, leaving just the variable on the left. 384 subtract 192 is 192. And now I need to divide away the 16. 16 times x would be a time to divide. And then 192 divided by 16 is 12. So I'm getting an x of 12. Now I'm always going to go back up here and plug in. Always, okay? So I've got 12 plus 12. 12 plus 12 is 24. Let's make sure that this figure is now proportional. 24 and 32 are the comparison, just as 12 and 16 are the comparison. These two ratios, these two fractions should reduce to the same value known as the scale factor. So let's do a little reducing here. 24 and 32 can both be reduced by 8. 24 divided by 8 is 3. 32 divided by 8 is 4. 12 and 16 can both be reduced by 4. 12 divided by 4 is 3. 16 divided by 4 is 4. Same reduction. Same reduction. So what that means is this is the scale factor. This is the scale factor, which means the figure on the left is 3/4 the size of the figure on the right. 3/4 its size. Okay, thanks for hanging with me in this video. I know it was a long one. I think you're going to do great. Keep working and let me know if you need any help. Happy studying.